All right, so we are now recording. I do have multiple batteries just in case this one happens to run out, but we will see how this goes. So,
big dog.
Big dog status.
I like that periodic table, the one that you're using.
yep, we'll get back to that in just a little bit. So, let's recap. Oops. Let's recap literally what we've done since Monday. Let's start out by talking about Lumic attractions. As far as the three things that you should have picked up from Lumic attractions, what are they? What are the three things that you should have?
Distance and stuff, right?
Distance and stuff. Tell me about distance.
Is distance increases, attraction decreases.
And in what way?
X, the
One
Square
half
thingy.
squared.
The inverse squared law. So
Yeah.
it drops off really quick. So as distance between charges increases, the force of attraction decreases by the inverse squared law, or basically drops off really fast. What else should you have picked up from the Lumic attractions that we discussed on Monday? Yes?
As the protons increase, the attractive force also.
Okay, as protons increase, the attractive force also increases, and that ends up being a linear effect rather than an inverse squared effect. All right, what was the third thing that we had mentioned from the Lumic attractions that you should have picked up from? Yeah.
The attractive forces are not spread between the electrons.
All right, so if you have electrons that are equidistant away from the nucleus, the force of attraction is not divided among those electrons. They are actually equally attracted to those protons in the center. Great, so then from there we ended up starting talking about the idea of, well, what would we have to do to remove electrons off of an atom? And we talked about photoelectron spectroscopy in the idea that if I were to bombard an element with X-rays, and we used high energy X-rays to the point where we were able to strip off all of the electrons off of something, not necessarily off of one particular atom, but all of them at some point in time will come off. We ended up getting a spectra, and that spectra looks like what we have up on the wall for potassium. And what can you tell me about the photoelectron spectra that you're seeing for potassium? What should we have picked up from that? Yeah.
It will have 4 rings of electrons.
Okay, it has 4, not rings.
But
I don't want to use the word rings because rings actually very specifically implies a path, a very distinct area that it goes into. It's not a ring. How did we define it? We defined it literally by the term energy level, right? Why are they in different energy levels at this point? In other words, how many energy levels do we have? We described this, well, this is the highest energy level, so this is the first energy level, this is the second energy level, this is the third energy level, and this is the fourth energy level. Why are these, or how did we separate these off by levels? What magic math did we use? Yes?
By power of 10, the difference of about power of 10.
Okay, so the difference between each of these is about an order of magnitude, or about power of 10. To go from first energy level to second energy level, we're at 347, going down to like 37 and 29, that is decreasing by a power of 10. Same thing for the next bracket, same thing for the next bracket after that. And it's going to continue in that same type of path if we were to look at other atoms further down on the periodic table. It generally ends up being an increase by an order of magnitude. All right, so if we were to start to summarize what we're looking at, we said energy level. Now, in the textbook, if I remember correctly, the energy level was defined as the letter N. To the best of my understanding, the College Board, at least according to their guidelines, are not going to be questioning you on the letters N, L, M sub L, or M sub S, which, for those people who are wondering, was the quantum numbers when you're taking the notes on it. If it said the principal quantum number was N, the azimuthal quantum number was L, and I can't remember what the M sub L stands for, but then there's the magnetic spin quantum number is the last one. Yes, sir?
So we'll only need to know the speed of the dumbbell and the clipper, right?
So that's the shapes, and we'll get to that in just a little bit. So all I was talking about is quantum numbers. Don't worry about quantum numbers. I'm not going to go over it too much. But if you were wondering how what I'm talking about relates to the quantum numbers from the textbook, energy level and N, same thing. So how are we defining an energy level once again based off of this data? How are we defining energy level based off the data that we have here? Yes?
The difference in magnitude between the electrons and the amount of energy required to rip them off.
So an order of magnitude difference in the energy needed to remove the electrons. So, an order of magnitude difference in the energy needed to remove electrons is what we're really talking about as an energy level. So then one of the things that we are going to be looking at as well is the fact that there happen to be multiple peaks in between the energy level itself. So if we're looking at those in there we go. If we're looking at these, how many peaks did I have in this first section? Uno. How many did I have here?
Dos.
2. And then here, eventually, we're actually even going to get a third one in this third energy level eventually, but we just haven't filled into it yet, but we'll talk about that in just a little while. As we're looking across this, what are we going to call the fact that there ends up being 2 peaks inside this second energy level? Why? It's kind of like it's been subdivided. If it's been subdivided, we would call that a sub-level. So, sub-level. By the way, the sub-level, for those people who are doing quantum numbers from the textbook, has an abbreviation of L. It also ends up being the azimuthal quantum number, which I am not concerned about. So, sub-level, which ended up being letter L, lowercase l. And we started defining this in detail yesterday, and there were 4 different sublevels. Type of sublevel. What are the 4 different types of sublevels that we talked about? S, P, D, F. Right?
Wait, so are there multiple, like, dumbbells and shapes within each energy level?
Yes.
So
let's actually take a look at how this is going to play out. Let me talk about the pattern. If I have a relationship between energy level and number of sublevels. Okay? If I have energy level and number of sublevels. If I have the first energy level, how many sublevels are there? 1. Which means it's really not a sublevel, it's just all the same thing.
that's because there's like no space, right?
There's no space, right? So if I have 2 second energy level, how many sublevels are there going to be? 2. Well, what is the first energy level going to be? In the first sublevel, in the first energy level, I have 1 sublevel. What's that sublevel going to be called? S. If I have a second energy level, I have 2 sublevels. What are those sublevels going to be called? S. And the second one would be a P. If I have 3 energy levels, how many sublevels will there be? 3. There'd be an S, a P, and a D. If I have 4 energy, the 4th energy level, how many sublevels are going to be within the 4th energy level? 4. How many people are starting to see the wonderful pattern that we're getting? No? Not so much. S, P, D, F. If we had 5, how many sublevels would there be? 5. What would be the 4 that you probably know? S, P, D, and F, and then the next one they theoretically have called G. Have we been able to stick any electrons into the G level orbital? Not yet.
Why not? Do we know what it looks like?
We'll get there. We'll actually have to get through the process to get to that point. All right, so now we've got, generally, you see the relationship between number of energy levels and the number of sublevels. Is that for each energy level, there is the same number of sublevels that are going to be divided within it. Why is it that I can fit more sublevels the further I get from the nucleus? Talk about it with your group. Why is it that I can get more sublevels the further you get from the nucleus?
Because of the area.
Yeah.
So if you're at energy level 3, that means you have 6 sublevels in total.
So then they're able
No.
to get more.
You have 3
So then
sublevels.
they're able to
In
knock
total.
out
Oh,
more.
in total, with all the sublevels going in. So yes, you'd have 1 in the first one, you'd have 2 in the second energy level, you'd have 3 in the third. So that means you'd have a total of 6 sublevels.
So in the third energy level, it's like the big circle, which is the S one,
Mhm.
right? Or the S, and then you have like the dumbbell thing. But where?
And all the clovers.
Where is the dumbbell shape in like relation to the sphere?
Inside the sphere.
Inside. So the S is the outermost, and then
No. Because the S and the P are both, the P orbitals are still going to be touching the outside edge of the S orbital. Imagine blowing up a balloon and tying it into a dumbbell shape. And taking those 2 balloons inside of another balloon that's completely spherical. And the outside edge of the dumbbell shape are touching the outside edge of it. Are they equidistant away from the nucleus? Yes. Okay. All right, folks. So, what was my question? It's always the hard part.
Why is there can there be more sublevels in
Yeah. Why can there be more sublevels for every energy level that we go down? We talked about this for about 15, 20 minutes yesterday.
Because it gets bigger.
What gets bigger?
Like the
Area.
radius of everything.
Not area.
Volume.
Area is a surface.
Volume.
Volume. For a small increase in radius gives you a huge increase in volume. So for each time that we go from an energy level to another energy level, I keep getting much more space because a small increase in radius gives me this huge increase in volume that allows me to fit more electrons into it. Now, if I'm trying to fit more electrons into that larger space, is it going to be able to fit in a easy, comfortable, normal-looking shape? No, because the gaps that are still left behind are in these bizarre crevices and corners around the atom itself. So this gets us to talking about the type of energy level. We've got S, P, D, and F. How many electrons can fit?
2.
In the S sublevel, I would get how many? 2. How many will I get in the P?
6.
And in D?
10.
F?
14.
14. Yeah.
if there's like a bunch, why do they end up being like weird shapes? If it's just a sphere surround, like
This is actually truly what I'm trying to get to right now, is trying to explain the shapes a little bit more. And literally it is the next step. Because what I wanted to explain next in this next column is, what can you tell me about column, in this next column I want to talk about how many orbitals do each of those sublevels have. And we haven't really talked about what an orbital is yet. So, how many orbitals in the sublevel? Okay, and I know that you probably tell me what the answer happens to be for it because we discussed this the other day, or you can do some simple math to figure it out. Let's just go ahead and fill this in so you have it, and then we'll start talking about the shapes once again and try and refresh your memory on how the shapes work. So if I have, how many orbitals are in the sublevel? How many orbitals are going to be in a S level? 1. How many different orbitals are there going to be in the P?
3.
3. How many are going to fit in the D? 5. How many in the F? 7. All right, so meaning that there's one spot where I can stick 2 electrons when I have an S. When I have a P, there's going to be 3 different spots where I can stick electrons, and I'm going to be able to fit 6 electrons into it, because each one of those spots can hold 2 electrons. Now this is going to be a quick review of something else that I discussed yesterday as well. I'm going to grab my water bottle for this. If this is an electron that's traveling at this roughly the speed of light, probably like a third of the speed of light, but it's going that way, and it's spinning like this, and we talked about the idea in physics that if you have a spinning, charged particle, what does that create?
Magnetic field.
Magnetic field. And I believe it goes by the right-hand rule. I could be wrong. My physics is rusty. And that means the magnetic field would be generated going that direction right now. That means there would be another electron that could actually be generating another magnetic field, but which way would that magnetic field be going?
In the opposite direction.
In the opposite direction. Okay? So that means, go ahead and mark this bottle and my bottle. so that way you can actually see the rotation in this. Stay.
What he does for physics or chemistry.
Which way is the small bottle rotating? Clockwise or counterclockwise? Counterclockwise. Which way is the big bottle rotating?
Clockwise.
Clockwise. Which means then one of them is forming a magnetic field this direction, the other one's forming a magnetic field this direction, which means that those two magnetic fields can roughly cancel each other out within that orbital, so they can actually kind of exist within that same space at the same time. So far, so good? Great. Then if I were to turn this around and go this way, both of them have changed the direction in which they are rotating just because they flip the direction in which we are looking at them. So it doesn't really matter which one's spinning which way. No, because both of them will probably flip back and forth on which one they happen to be spinning. As long as one is spinning one direction, the other one is going to be spinning the opposite in order to make sure it counteracts the magnetic spin. Yes?
So if the magnetic spin is counteracted and they're both electrons, and like why don't they like repel each other?
They do repel each other because of their overall charge, but the spinning charge will help keep it attracted because, or not keep it attracted, will help cut down and mitigate the repulsion when the magnetic fields that are being generated are counteracted. So let me try that again. One's creating a magnetic field going this way, one's creating a magnetic field going that way. They still have charged particles. They're still both negative and will repel because they're negative. But at least their magnetic fields that are being generated because of the electrons themselves spinning will not add to the repulsive force. They will actually be neutralized by the fact that they're going in opposite directions. Yes?
What happens if you only have one electron and it's creating its magnetic field and you don't have another electron to cancel it out?
Good question. If you have enough of them all traveling in the same direction, the material itself becomes magnetic.
That's why we have magnets.
That's actually why some materials can be attracted to magnets or be turned into magnets. Because if you get all the atoms to be, or you can not get all of them, but a good majority of the electrons to be spinning all in the same direction, the entire material can then become magnetic. Which elements are really prone to being able to do that easily? Iron.
That's it.
Well, there's another handful. Iron, cobalt, nickel. Those are the three major ones that, as elements, are very easily attracted to magnets. We're not going to get into para or diamagnetism. I will let you save that for a future time in a science class later, because unfortunately we don't have time. I believe it is in the textbook, though. If you ask me later, I'll be happy to tell you where it's at. Okay. All right, so we got this part down. And the part that I have a feeling that was confusing people yesterday was the shapes and how the shapes are being generated and what is an orbital. Okay? So
Show us that really awesome YouTube video.
I could show you the picture. We could watch the bad YouTube video again. What I'd like to do instead is, instead of showing you that, I wanted to show you a couple pictures. And let me describe the picture first. When you were in your previous chem class, I think one of the labs that a lot of you probably did is you took a piece of steel wool and you zapped the steel wool with a battery.
Yes.
How many people remember zapping a piece of steel wool with a battery? Not that many. Got it. You zap a piece of steel wool with a battery, it actually sets on fire. When it starts to set on fire, it glows in a really cool place, and it can also even throw some sparks off of it as well. Now, if you end up adding extra air to it, it'll burn even brighter and glow even brighter and burn faster, okay? Because you're adding more air, you're speeding up the chemical reaction because you're increasing the concentration. We can talk about the kinetics, but we won't. Now imagine that I were to take a ball of stainless steel and stick it into a cage. Then I tie that cage to a chain that I can then spin. And right before I start spinning it, I zap it with the battery so it's on fire, and then I'm spinning it. Everybody with me so far on the image that I'm trying to create?
Yes.
Okay, reason I want to create this image in your head is because there's a number of people who have done time-lapse photography. And with that time-lapse photography, they have been able to get pictures of people, let's see, burning steel wool, time-lapse. There we go. Or long exposure, sometimes it's called long exposure photography. Let me take a look at images. So here's a bunch of different people that have made images of not time lapse.
Long exposure shots.
Long exposure photography. This is probably one of the ones that I wanted to show you so you can actually see it in full. Let me show the image. Image it. There we go. Let me zoom that down so you can see the whole thing. Great. So let me describe on how they made this image to begin with. So you've already got the general idea about the cage, right? The cage itself is somewhere in this circle. But they did a delayed photography of this, where they did a long exposure. How many people know what a long exposure photography means? Just means you leave the shutter open for a longer period of time so it can absorb more light. Which means anytime you start moving, you show up as a blur. So if you actually look at the guy in the center, you'll notice that you see he's been standing pretty still, except his hand is a blur. Notice that his hand is kind of like a, rather than really distinct, fingers or hands or gloves that happen to be sitting in there. It's because he's spinning his arm. And it's blurred that entire section because it was a long exposure. By the way, for those people interested, your cell phone, if you have the App Store and you can go onto the App Store, if you typed in long exposure into the Play Store or App Store or whatever, chances are there's an app that you can actually download to turn your own camera into a long exposure camera and take shots similar to this. Are they going to turn out as nicely? Probably not. These were probably done with professional photography equipment with like digital single lens reflex cameras. That said though, guy in the middle kind of blurry. Right now, do we see the actual cage in which the steel wool is contained? No. What do we see? We see a nice big broad path that it ended up taking. What else do we see? We see all the extra sparks that have flown off of that steel wool, and it's actually colliding. And what I don't know if you can see at the moment, he's doing this underneath the bridge. Do you get it? Because underneath the bridge is that archway, and he's spinning it underneath the archway, and the sparks are flying off, and then hitting the archway underneath the bridge to illuminate that outside edge. So what you're seeing is all this is hitting the outside edge, hitting the ground, and you can tell that's even a road because there's a curve. You can even see the lift to the curve on both sides. And then what you see is the actual path that the steel wool is taking. Here's the big difference. This is a long exposure shot. Can I tell where the ball happens to be right now?
No.
No. If I took a snapshot, what would this picture look like? Talk about it with each other. If you took a snapshot, not a long exposure like this pretty picture, but if you took just a snapshot, what would it look like? Talk about it with each other.
It'd be like a
Depending on how fast it's spinning and how fast
Plus you don't think
It's nap time.
All right, folks. If we were to take a snapshot of this, what would you see? Yes.
The individual, metal cage.
You would see just the individual metal cage. Would you get this entire circle?
No.
No. What you'd probably get is one little piece right here. You might be able to see the string go into his hand, and you might get a little bit of trailing and some of the sparks that are flying off of it. Actually, it's probably going in this direction. You might see a couple of the sparks flying off of it, but you would not get the image of the entire circle. Everybody with me so far? The cage is the electron. The orbital is the circle. Everybody grab onto that? The orbital is the circle. Does the circle exist without the cage? No. The electron itself is going to be traveling in that path. Is it going to make that shape if the electron's not there? No. It's just going to be empty space that's sitting out in the middle of nowhere. But if I put that empty cage on the inside of it, I can make that shape happen. So now, with all that, what's an orbital? I'm not going to make you come up with that definition. So, what is an orbital? It is a wave formed by the path of an electron.
What's a wave? Right, but when they're talking about it in the book, etc., they're like, I don't think it's the same type of wave.
Here's the problem. The wave that I just drew on the wall ended up being two-dimensional. It was able to go front to back and up and down. When we're talking about the waveforms that an electron can make, what shape are they going to be able to take?
Like front or 3D.
Three-dimensional. It can go up, down, left, right, and forward, back, right? So it can go in all 3 dimensions. Now, I think there were some other long exposure shots that people had taken in which they tried to make a sphere. Yeah, here's kind of one, but I think they more or less moved. But you notice how it's kind of forming into a ball? My guess is that they were sitting there doing one of these kind of things and trying to make a big sphere around themselves, or maybe they were spinning it and changing the length of the string or something. I'm not sure. Some of them, what I'm trying to figure out, though, is can you break this into a 3-dimensional pattern rather than just a 2-dimensional pattern? By the way, how about this? Can you tell what happened here?
Mm-hmm.
What'd he do?
It flew off.
Okay, so he let it go, spun it, and then let it go, and you can see the arc that it ended up forming when he did it. I like this one quite a lot. Okay? Why do I like that one quite a lot? Because you can see he's standing on something that ends up having a reflective surface underneath it.
It's the eye of Sauron.
It's like half a foot. Half
The
a
double.
What I was hoping to find is sometimes there are some people who try to make a 3-dimensional version where it's not just constantly in a plane, but that ends up being very hard to actually make on your own and make it happen. The best one that I saw was that one that would kind of look like a sphere that was above it. That was above this. So the question that I believe that Sarosh ended up asking that I have done a very poor job at answering is, what is the wave formed by an electron?
Like, I don't understand what they mean by a wave.
Okay, so you can picture a wave in 2 dimensions, correct? The hard part is picturing what that wave is going to look like in 3 dimensions. What does a wave look like in 3 dimensions when you're talking about something that is being contained by the protons? Ultimately, how much of that do you actually have to be able to visualize? Close to 0. Okay? What do I mean by that? Going back to the different sublevels that we've been talking about. What were the shapes that we talked about yesterday when it came to the different sublevels?
Dumbbell, sphere.
Dumbbell, sphere, clover.